Okay, today we're going to be looking at a spring-mass-dashpot system. Namely, we're going to use a Laplace transform to arrive at a solution. So a spring-mass-dashpot system consists of a block with mass m. It's tied to a dashpot with a damping coefficient c and a spring with spring constant k. In this situation, we're going to have an external force that's being applied. And the external force is going to be applied for 1 unit of time and with a magnitude of 1. Also, our initial conditions are x of 0 equals 0 and x prime of 0 equals 0. So the system begins at rest and is not moving. And then it feels this external force, and then it's released. Okay, so looking at the free body diagram, so the net force on this object is mass times acceleration. Fs is the spring force, which is defined by Hooke's law as being proportional to the amount that the mass is displaced. And the force due to the damping force due to the dashpot is proportional to its velocity. Okay, so how do we show an external force that's only applied for 1 second? Well, we need to make use of something called the unit step function. So the unit step function is defined as follows. So the unit step function is not really a function because it's discontinuous at a. It's defined as being equal to 0 when t is less than a, but then jumps up to 1 when t equals a. So we can make use of that here by writing this. So you can see here that when t is less than 1, this term here is 0, meaning that the applied force of 1 is being applied. But then as soon as t equals 1, representing the amount of time that the force was applied for, this term here will equal 1. So 1 minus 1 is 0. And that shows that after t equals 1, the external force is removed. So if we let the mass of the block equal to 1, the spring constant equal to 100, and then the damping coefficient equal to 2, our differential equation looks like this. Okay, so we're going to take the Laplace transform of this. And since our initial conditions are 0, it makes taking the Laplace transform much easier. Which is why I chose them to be 0. Okay, so this is the Laplace transform of x double prime with 0 initial conditions. This is the Laplace transform of x prime with 0 initial conditions, and this is the Laplace transform of x. Laplace transform of x of t is x of s. So now what about the right-hand side? Well, the Laplace transform of 1 is just 1 over s. And the definition of taking the Laplace transform of the unit step function is okay, so with the unit step function here, we can think of it as being multiplied against 1. So you can see the Laplace transform is just the Laplace transform of 1 multiplied by multiplied e to the minus a s. In this case, a is 1, so we end up with this. Okay, so next we want to put everything in terms of s on the right-hand side. Okay, so from now on I'm not going to write all of these terms here. I'm just going to write a function of s here, f of s here, just to simplify things for myself. Okay, so for this, we need to complete the square in order to turn this into something that we can actually work with. So the denominator there is actually equal to, so a quick check, when s is 0, this term here is 100, and when s is 0 here, this term here is 100. So these two things are equivalent. So the first thing we need to do is partial fraction decomposition on that guy right there. So in order to do that, we need to break this up into this. So in order for these two things to be equivalent, then if we put them over a common denominator, then their numerators have to be equivalent. Okay, so I'm just going to do this really quick. But a really easy way to do this is first set s equal to 0. When you do that, you plug s equals 0 here, this term disappears, and s is 0, 1 plus 99 is 100, so you can solve for a as being 1 over 100. So similarly, to solve for b and c, although it's not as apparent, but if you chug your way through the calculations, you can see that this works out. If you let s equal the complex number minus 1 plus the imaginary number I times root 99, when you plug that in here, this term will vanish. We'll end up with a complex number over here. When you solve for the real and imaginary parts of the complex number, you can easily solve for b and c as. So hopefully those are right. If you notice that they're not right, then please let me know. But the solution seems to work out. Okay, so when we do partial fraction decomposition on this term here, we end up with this. Okay, so this is where working with the Laplace transforms gets a little tricky, because when we take the inverse Laplace transform of all these terms over here, to make it easier, we want to have terms over here that we can recognize. So, for example, we recognize the Laplace transform of 1 as being 1 over s, so this term here is fine. But what about this term? Well, with the s plus 1 here, it looks close to the Laplace transform of a shifted cosine function, but in order for it to be the Laplace transform of a shifted cosine function, there also needs to be a plus 1 up here indicating that it's been shifted. So we're going to have to adjust this without changing the overall formula in order to have a term here that we can work with. Similarly here, this looks like the Laplace transform of the sine function has been shifted, but it's missing the root 99 up here, so we're going to have to put that in order to take the inverse Laplace transform of this. So we can't just put plus 1 and root 99 here. All the algebra that we have to do has to be completely legal. So what we do is in order to add 1 here, we also have to subtract 1. So the way that we do that is as follows. Okay, so we've simplified our lives quite a bit here. Sorry to rush through that. But each of these terms here are now recognizable as the Laplace transforms of functions that we know. So when we take the inverse Laplace transform of all these terms, we end up with x of t, which is the mass's position with respect to time, which is what we're looking for. Okay, so the inverse Laplace transform of this term here is 1 over 100. The inverse Laplace transform of this, as mentioned, is the shifted cosine function, which looks like this. Similarly, I should mention too that when I say the shifted cosine and shifted sine function, I don't mean that sine is being shifted, I mean that its Laplace transform is shifted like this. Okay, so what about this other side here? Well, earlier we said that when you have a Laplace transform of a function and it's being multiplied by e to the negative as, then that means that you must have taken the Laplace transform of a function that's been shifted by a and is being multiplied by the unit step function. Okay, so we're going to use this here in order to solve for the terms that are in here. Now, all the terms that are in here are the same as the terms that showed up here. So what I'm about to write here is it's going to look like what you see here. The only difference is that they're all shifted 1 and they're all being multiplied by the unit step function. It's pretty straightforward. So this is the result that we're looking for. This is x of t. You can see that when t is between 0 and 1, these terms here are turned off, and x of t just consists of these 3 terms. But as soon as t equals 1, these terms turn on, and the behavior of x of t suddenly changes. So let's open up MATLAB and plot this in MATLAB and have a look at the result.
Okay, so I'll run the little animation so you can see what's going on. Here we go. Okay, so as you can see, as the force is being applied, the mass moves away from its equilibrium position, and it begins to reach a new equilibrium position. But then as soon as t equals 1 and the force is removed, you can see that because of the big spring constant, the mass accelerates rapidly back towards its original equilibrium position, but overshoots it. And thanks to the dashpot and its damping effects, instead of oscillating forever, the mass will eventually reach a new equilibrium position.